Video, let me take one numerical on Z transform. A stable and causal LTI system described by the difference equation y of n plus 0.25 y of n minus 1 minus 0.125 y of n minus 2 is equal to minus 2x of n plus 1.25 x of n minus 1. Find the system impulse response. So in this example, the difference equation is given. We supposed to find the impulse response. Here we need to follow the following steps. The first step is we supposed to find the Z transform of given difference equation. That is, first step is find Z transform of given difference equation. So once if you find the Z transform, the second step is we have to find y of z divided by x of z ratio, which is nothing but h of z, that is system transfer function. Then the third step is we supposed to take inverse Z transform of h of z to get the impulse response h of n. That is, find inverse Z transform of h of z to get impulse response h of n. Now let me find the Z transform of given difference equation. So here the given difference equation is y of n plus 0.25 y of n minus 1 minus 0.125 y of n minus 2 is equal to minus 2x of n plus 1.25 x of n minus 1. So we know that the Z transform of any discrete sequence x of n is x of z. The Z transform of x of n minus n naught, that is shifted signal of x of n by unit n naught, is given by z power minus n naught x of z. That is shifting property of Z transform. Now we supposed to, by applying shifting property of Z transform, we can find the Z transform of given difference equation. So we'll call it as equation 1. So apply by taking Z transform of equation 1, that is the Z transform of y of n is y of z plus 0.25. Here it is y of n shifted by 1 unit. So here n naught value is 1. So we can represent it as z power minus 1 y of z. That is z power minus 1 y of z minus 0.125 z power minus 2 y of z is equal to, on right hand side we have minus 2. Z transform of x of n is x of z plus 1.25 z power minus 1 x of z. Now let me take y of z as a common factor here. Y of z 1 plus 0.25 z inverse minus 0.125 z power minus 2 is equal to, here I will take x of z as common factor, x of z minus 2 plus 1.25 z inverse. So now let me take y of z by x of z. Y of z divided by x of z is equal to minus 2 plus 1.25 0.25 Z inverse divided by, we have 1 plus 0.25 Z inverse minus 0.125 Z power minus 2. And we know that the ratio of y of z divided by x of z is nothing but system transfer function, that is h of z. So now we found h of z. Now by taking inverse z transform of h of z, we can easily find impulse response, that is h of n. Now let me find inverse z transform of h of z. So here h of z is minus 2 plus 1.25 z inverse divided by, we have 1 plus 0.25 z inverse minus 1 z power minus 2. So now find inverse z transform of h of z by using partial fraction method. So now let me represent this h of z as h of z is equal to minus 2 plus 1.25 z inverse. I will try to find the roots of this quadratic equation in terms of z inverse. That is, we'll get 1 plus half z inverse 1 minus 1 by 4 z power minus 1. So here the variable is z inverse. We can find the roots directly by using the calculator. In calculator, keep the calculator in degree mode and enter the coefficients in decreasing order, that is minus 0.125 and 0.25 and 1 will get 2 and 4, that we have to write in inverse form, that is 1 upon 2 z inverse 1 upon 4 z inverse, and we have to change the sign also. If it is minus 2, we have to take it as plus 1 by 2 z inverse, and for this we'll get plus 4, we have to write it as minus 1 by 4 z inverse is equal to minus 2 plus 1.25 z inverse So I will represent it as, I will try to find this inverse z transform using partial fraction method, that is k1 divided by 1 plus 1 by 2 z inverse plus say another constant k2 divided by 1 minus 1 by 4 z inverse, or I can represent it as, we have 1 plus 1 by 2 z inverse 1 minus 1 by 4 z inverse. So here we have 1 minus 1 by 4 z inverse k1 plus k2 1 plus half z inverse. So now comparing RHS and LHS, I can represent it as minus 2 plus 0.125 z inverse is equal to, that is numerator is equal to numerator term, that is 1 minus 1 by 4 z inverse, we have k1 plus another term is 1 plus 1 by 2 z inverse k2, 1 plus 1 by 2 z inverse k2. Now to find the constants k1 and k2, we have to make any one term is equal to 0. So if put here, I will take z inverse is equal to 4. If you take z inverse is equal to 4, so here this 4 divided by 4 will become 1, 1 and 1 will get cancelled, so entire term k1 will become 0. then we can easily find K2. So substituting Z1 is equal to 4 in this equation, I can get minus 2 plus 0.125 into 4 is equal to, here this term will become 0 plus 1 plus 1 by 2 into 4 K2. So therefore K2 will be equal to, here simplifying this term will get minus 1.5 divided by, we have 3 here, that is 4 divided by 2 is 2, 2 plus 1 is 3, therefore K2 will be equal to minus 0.5. So now similarly, now try to make K2 term equal to 0. To make K2 term equal to 0, we have to choose Z inverse equal to minus 2. That is, put Z inverse equal to minus 2. Therefore, I can write it that this equation as minus 2 plus 0.125 minus 2 is equal to, we have 1 minus 1 by 4 minus 2, and this entire term will become 0. So this will be minus 2.25 is equal to, so here it will be 1.5 K1. Therefore K1 is equal to minus 2.25 divided by 1.5. So simplifying this, we'll get K1 is equal to minus 1.5. Therefore now I can represent H of Z is equal to K1, that is minus 1.5 divided by 1 plus half Z inverse plus, and we have K2 is minus 0.5 divided by 1 minus 1 by 4 Z power minus 1, or I can represent it as H of Z is equal to minus 1.5 divided by 1 minus 1 by 2 Z inverse plus, we have minus 0.5, 1 minus 1 by 4 Z inverse. So now by taking inverse Z transform, of H of Z, will get H of N is equal to, this is minus 1.5 is constant, inverse Z transform of 1 upon 1 minus half Z inverse will be given by minus 1 by 2 power N U of N plus, here we have minus 0.5 1 by 4 power N U of N. So this is the required impulse response of the system.